Hello, everyone. Tonight we begin a journey not of miles, but of molecules. We're going to travel inwards into the unseen to the very fabric of existence. Close your eyes and imagine you are standing at the very edge of time at the beginning of everything. There is no sound, no light, no form, just a swirling, energetic void. Then, with a sigh quieter than a whisper, something shifts. The first atoms begin to form. They don't explode or shimmer with fanfare. They simply emerge like thoughts in a sleeping mind. Tonight, we will follow their story from their quiet beginning to their endless dance. This journey is a safe one, and I'll be here with you every step of the way. But I must issue a gentle but very real warning. The things we are about to explore are so vast and ancient, you might not survive the first few paragraphs. The sheer scale of it all might just lull you into a deep sleep. Now, before you go and watch, please take a moment to like and subscribe to this video, but only if you truly enjoy what I do. And if you're comfortable, feel free to share in the comments where you are in the world right now and what time it is for you. I find comfort in knowing that as I speak somewhere across the globe, someone is settling in, ready to float on these words. Our story begins in the vast, elegant silence of the early universe. It's a place no one has ever truly seen, a time no human has ever known. But we can deduce its nature, piece it together from the faint echoes and lingering whispers that still resonate across the cosmos. This wasn't a loud, chaotic birth. The Big Bang. The name we give to this moment was not an explosion in the traditional sense, but a rapid expansion of space itself. In the first moments, there were no atoms, no elements, no galaxies. There was only a superheated, dense primordial soup of energy and fundamental particles, quarks and gluons and leptons. They flitted about in a state of wild, untethered freedom, unable to form anything stable. It was a kind of cosmic childhood, full of raw, untamed potential. But as the universe expanded, it cooled. And as it cooled, the laws of physics began to settle in like a quiet dawn over a landscape. The wild energy subsided, and for the first time, these tiny particles could begin to form partnerships. Quarks, drawn together by a force more powerful than we can truly grasp, bundled themselves into protons and neutrons. These were the first building blocks of matter, as we know it, the very core of what would become everything. They weren't complex, they were simple, stable, and ready to wait for their next partners. For hundreds of thousands of years, the universe was a quiet, dark place. The protons and neutrons, now huddled in their nuclei, couldn't yet form atoms. The universe was still too warm, filled with a dense fog of electrons and photons that would immediately break apart any nascent atomic bonds. This era, a historian might say, was the Great Wait. The fundamental particles existed, but the grand architecture of elements was not yet possible. The universe was a library filled with books, but all the words were jumbled, illegible. Then a cosmic milestone. The temperature dropped just enough. At around 380,000 years after the beginning, the electrons were finally able to settle into a stable orbit around the nuclei. This moment, known to astronomers as recombination, was a profound chemical event. Hydrogen and helium, the two lightest elements, were born. For the first time, the universe was transparent. The light, which had been trapped and scattered by the dense fog of electrons, was finally free to travel. This ancient light, the cosmic microwave background as we call it, is still bathing the universe today, a faint, gentle glow that whispers of the quiet moment when atoms first emerged. So in the immense silence of deep space, our first two characters arrived: hydrogen and helium. Hydrogen, with its lone proton and electron, was a restless spirit eager to bond and form new things. Helium, with its full complement of two protons, two neutrons, and two electrons, was perfectly content with itself, a true cosmic introvert already in a state of quiet equilibrium. It's a good time to mention a little-known fact about these cosmic beginnings. While hydrogen and helium were the main players, A tiny fleeting amount of lithium was also formed in this primordial mix. For a moment, it was one of the universe's most common elements. But its moment in the spotlight was brief. It would later become much more rare, destined for a role in batteries and medicine, a quiet, almost forgotten star of the first moments. For a long time, nothing much happened. The universe was a vast, cold expanse of these two simple gases, drifting and expanding. But gravity, that patient sculptor of reality, was quietly at work. It pulled the gas clouds together slowly over millions of years into denser clumps. In these clumps, the pressure and temperature began to rise. A new kind of chemistry was about to begin. A fiery, transformative chemistry. Eventually, the pressure and heat in the centers of these protostars became so intense that the nuclei of hydrogen atoms began to fuse. Not to bond in the way we've come to think of it, but to meld to become one. This process, nuclear fusion, is an entirely different kind of reaction. It's a fundamental change in the very heart of the atom. 4 hydrogen nuclei squeezed together under unimaginable pressure would become a single helium nucleus. And in that process, a tiny bit of mass would be converted into an immense amount of energy, according to a famous equation. The star ignited. A universe that had been dark and cold for ages was suddenly filled with light. From this point on, stars became the great chemical forges of the cosmos. They weren't just balls of light. They were alchemical factories, taking the simplest ingredients, and through patience and immense pressure, creating something new. Our sun, a modest star, spends its life turning hydrogen into helium. This process is so slow and steady that it will last for billions of years, a constant, predictable, and remarkably gentle reaction. But in larger stars, the story becomes more dramatic. Once a massive star has exhausted its hydrogen fuel, it begins to burn helium. The core shrinks and heats up, and the helium nuclei fuse to form carbon. Then carbon fuses into oxygen, and so on. The star becomes layered like a cosmic onion with a shell of each successive fusion reaction, happening as it builds heavier and heavier elements in its core. It's a process that builds the elements that will one day form planets, oceans, and living beings. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the heart of a star that lived and died long ago. And sometimes a star's death is the most magnificent chemical event of all. When a massive star has created a core of iron, the fusion process ends. As a historical note, ancient alchemists spent centuries trying to turn lead into gold, believing in a kind of chemical magic. They were correct in their assumption that one element could become another, but they were working on the wrong scale. The true alchemy happens not in a crucible, but in the heart of a collapsing star. The sudden loss of energy in the iron core causes gravity to win. The star collapses in on itself and then explodes in a brilliant fleeting event we call a supernova. In that explosion, in a flash brighter than 100 billion suns, the final elements are forged. The immense energy of the blast creates all the elements heavier than iron, gold, platinum, uranium, the very stuff of our jewelry and our technology. So you see, you and I are made of stardust. This isn't just a poetic notion. It's a profound chemical truth. The atoms that make up your body have been on a vast cosmic journey. They were born in a star scattered across the galaxy in a supernova, and then, a few billion years later, pulled together by gravity to form a nebula, then a solar system, and finally a planet. And on that planet, in a quiet, secluded corner of the Milky Way, those atoms found their way into a living, breathing being. The oxygen you breathe right now has had a long, long way to go to get to your lungs. It's a thought that, for me, brings a deep sense of peace. The story of the first atoms is one of patience and quiet transformation. It is not a tale of thunder and lightning, but of cooling settling and the gentle, persistent pull of gravity. It is the story of how nothing became something, and from that, something, a universe of quiet, constant, and beautiful chemistry began to unfold. We are but a late chapter in that ancient book, a brief, curious arrangement of particles that have been on a journey for billions of years. Rest easy, knowing that you are a part of that journey and that the same forces that built the stars also built you. The universe, remember, is now filled with an exquisite cast of characters. From the simple hydrogen to the intricate gold, all the players are present waiting for their parts. But these actors don't perform alone. They seek partnerships, alliances, and connections. In the quiet language of chemistry, we call these connections chemical bonds. These bonds are the very architecture of everything, the unseen glue that holds atoms together, transforming individual entities into molecules and matter. They are the reason you can touch the screen you're looking at, and they are the reason your own body is a solid, beautiful thing, not just a drifting cloud of particles. To understand bonding, you first have to understand the most social of the particles, the electrons. Specifically, the electrons in the outermost shell, the ones we call valence electrons. They're the ones that get all the action. An atom, you see, is most comfortable when its outermost shell is either completely full or completely empty. It's the atomic equivalent of being debt-free or having a full wallet. It brings a sense of stability. Atoms will do just about anything to get to that state, and that desire for stability is the driving force behind all chemical bonding. There are a few ways for atoms to get what they want. The first is a classic case of sharing a kind of chemical socialism. This is the covalent bond. Imagine two atoms, like two small children with a favorite toy. Neither wants to give it up, so they decide to hold on to it together. In a covalent bond, two atoms share a pair of electrons. Each atom contributes one electron to the bond, and the electron pair now belongs to both, satisfying both of their desires for a full outer shell. This is a common arrangement, especially among nonmetals. For instance, think of water, a molecule we'll get to know very well. One oxygen atom and two hydrogen atoms. The hydrogen atoms each have one electron they'd like to share, and the oxygen atom needs two to complete its outer shell. So each hydrogen shares its one electron with the oxygen, and in return, they get to count two of oxygen's electrons in their own shell. It's a cooperative, stable arrangement. These bonds are strong and directional, creating precise, elegant shapes. A quick historical diversion: for a long time, scientists had no real idea what held molecules together. It wasn't until the early 1900s that physicists like G.N. Lewis and Linus Pauling began to develop the concept of shared electrons. Lewis, a prominent American chemist, introduced a simple diagram to represent valence electrons, the familiar dot structures that still help students understand bonding today. But it was Pauling who, in his groundbreaking work, The Nature of the Chemical Bond, described the different types of bonds with such clarity that it became the foundation of modern chemistry. This book, published in 1939, won him the Nobel Prize and changed the way we think about the very nature of matter. Now, not all atoms are as polite as those in a covalent bond. Sometimes one atom is a little bit of a bully. It wants electrons so badly, it just takes them outright. This leads to the ionic bond, a kind of chemical transaction, rather than a partnership. This happens when there is a significant difference in a property called electronegativity, an atom's tendency to attract electrons. Let's revisit our friends sodium and chlorine. Sodium has a low electronegativity and is quite happy to get rid of its single valence electron. Chlorine, on the other hand, has a very high electronegativity. It's practically a vacuum for electrons. When they meet, sodium willingly gives its electron to chlorine. Sodium, having lost a negative charge, becomes a positively charged ion. Chlorine, having gained a negative charge, becomes a negatively charged ion. These two oppositely charged ions are then powerfully attracted to each other like a pair of celestial magnets. This electrostatic attraction holds them together, forming a salt crystal. It's a clean, decisive kind of relationship. One of the unique and curious details about ionic bonds is the solid state they create. The ions in a crystal are arranged in a perfectly ordered repeating grid. These precise geometric structures are what makes salt crystals so beautifully cubic, and they are also what makes them so hard and brittle. You can't bend a salt crystal. You can only break it. It's a rigid but stable kind of existence. Finally, there's a third, much more casual kind of bond found only in metals. This is the metallic bond. Picture a huge crowded party where no one is really paired up. Instead, everyone's outer electrons are just wandering freely through the entire space, a kind of communal electron sea. The positively charged atomic nuclei are all sitting in this sea, attracted to the free-floating negative charge all around them. It's a different kind of stability, not a rigid partnership, but a fluid communal one. This electron sea is what gives metals their unique properties. Because electrons can move so easily, metals are great conductors of electricity and heat. When you pass an electric current through a copper wire, you're really just nudging that electron sea along a kind of subatomic conga line. The same fluidity is why metals are malleable and ductile. They can be hammered into thin sheets or pulled into wires without breaking. The atoms can shift positions, but the communal bond remains unbroken. So you see, even at the molecular level, relationships have different dynamics. There are the generous co-op shares of covalent bonds, the clean transactions of ionic bonds, and the fluid communal mingling of metallic bonds. And all of it is driven by one simple silent truth. Atoms are seeking stability. They are looking for a state of lower energy, a place to rest and be at peace. When atoms come together to form a bond, they release energy moving from a higher energy solo state to a more comfortable bonded state. It's the atomic equivalent of collapsing onto the couch after a long day. But these are not the only ways that atoms interact. There are also weaker, more temporary attractions, like the kind we'll see with water. These are what hold things together in the quietest, most subtle ways, and they are the subject of our next chapter. A great argument among theoretical chemists still rages on about whether or not some of these lesser bonds should truly be called bonds at all, with one side arguing that any attraction that holds a structure together deserves the name, and the other insisting on more rigorous definitions. This is a debate for the wide awake, but for our purposes, we'll just refer to them as elegant connections. Our journey through the elements and their bonds has brought us to a strange and beautiful place. We've seen atoms link and share, give and take, all in the pursuit of stability. But one molecule stands out, a humble, simple V shape that defies every expectation and holds the secrets of life itself. We are now in the gentle, watery world of H2O. On the surface, water seems simple. A single oxygen atom bonded to two hydrogen atoms. You would think, based on its small size, that it would be a gas at room temperature like methane or ammonia. Yet it's not. It's a liquid, a fact so common we barely notice it, but a profound mystery to a physicist in another galaxy. The reason lies in a quiet, invisible force that is not quite a bond, but more like a handshake that atoms can't let go of. Remember how we talked about electronegativity and atoms' desire for electrons? Oxygen is a particularly greedy element. It pulls the shared electrons in the water molecule's covalent bonds closer to itself, like a quiet game of tug-of-war. This gives the oxygen side of the molecule a slight negative charge and leaves the hydrogen ends with a slight positive charge. The molecule is now polar, a tiny electrical magnet with a positive and a negative pole. And because opposites attract, the slightly positive hydrogen end of one water molecule is drawn to the slightly negative oxygen end of another. This attraction is called a hydrogen bond, and it is one of the most important concepts in all of chemistry. It's not a strong bond like the ones that hold the atoms together within a molecule, but it is strong enough and numerous enough to hold trillions of water molecules together in a vast, intricate, and ever-shifting network. This is why water is a liquid at room temperature. It's because of all the tiny magnetic handshakes between the molecules. This network gives water some of its most peculiar and life-giving properties. First, its high specific heat capacity. This is a measure of how much energy a substance can absorb before its temperature rises. Water has an incredibly high specific heat capacity, which means it can absorb and store a huge amount of heat. This is why coastal cities have milder climates than inland ones. The ocean, a vast body of water, acts as a thermal cushion, absorbing heat in the summer and releasing it slowly in the winter. For life, this is a lifesaver. It protects us from extreme temperature swings, keeping our planet a gentle, habitable place. A fun historical side note. The ancient Egyptians, in their wisdom, had a unique understanding of water's properties. While they didn't have the modern concept of hydrogen bonds, they observed water's ability to cool things down. They would use special porous clay jars to store water. As a small amount of water seeped through the clay and evaporated from the outer surface, it would absorb heat from the rest of the water, cooling the contents inside. It was a simple, elegant application of a physical principle long before the science was understood. A cool drink on a hot day, courtesy of the quiet magic of evaporation. Now for water's most famous and strange party trick, it expands when it freezes. Every other substance on Earth contracts as it solidifies. The molecules get closer and more dense, but water, as it cools, arranges its molecules into a perfect, elegant, hexagonal lattice. This geometric arrangement, held together by hydrogen bonds, actually takes up more space than the jumbled, chaotic liquid state. So ice is less dense than liquid water, and it floats. The consequences of this are enormous. If ice sank, lakes and oceans would freeze solid from the bottom up, killing all aquatic life and changing the Earth's climate forever. Instead, ice forms a protective, insulating layer on the surface, preserving the liquid water below and allowing life to endure. The debate among physicists and chemists about the precise structure of liquid water is a long-standing one. Is it a continuous network, a collection of small clusters, or something else entirely? The truth is, we don't fully know. It's a bit of a chaotic quantum dance, with hydrogen bonds constantly forming, breaking, and reforming in milliseconds. This is a question for the wide awake, but the mystery of it makes water all the more beautiful. Water is also known as the universal solvent, and it's this ability that makes it essential for life. Its polarity allows it to dissolve an enormous range of substances. When you drop salt into a glass of water, the positive sodium ions and negative chloride ions are pulled apart and surrounded by water molecules, a process called hydration. Water's tiny magnetic poles tug at the ions, breaking them free from the crystal structure and pulling them into solution. This is why water can transport nutrients in your blood, why plants can pull minerals from the soil, and why it can clean a dirty dish. Water is a molecular taxi service, picking up all sorts of passengers and carrying them wherever they need to go. Of course, water isn't perfect. It is notoriously bad at dissolving nonpolar substances like oil. That's a good thing, though, because it's this resistance that allows our cell membranes, made of a fatty nonpolar layer, to hold their shape and not dissolve in the water that fills our bodies. The rule is simple: like dissolves like. Polar substances dissolve in polar solvents, and nonpolar substances dissolve in nonpolar solvents. This elegant separation is the very reason oil and vinegar dressings separate, and why soap, which has both a polar and a nonpolar end, is so useful for washing greasy hands. Water's quiet influence is everywhere. It shapes the land through erosion. It sculpts our weather, and it provides the medium for all the complex chemistry that happens inside us. Your body is over 60% water. The blood flowing through your veins, the fluid in your cells. The tears you shed, all of it is water holding everything in a delicate, life-sustaining balance. The water molecules in your body are constantly forming and breaking those gentle hydrogen bonds, whispering secrets to each other as they carry out their countless tasks. So the next time you take a sip of water, or watch a snowflake fall, or listen to the quiet drip of a faucet, remember the profound mystery of this simple molecule. Its oddities are not flaws. They are the very things that make it so perfect for life. Its willingness to cling to itself, to expand when it freezes, and to dissolve almost anything, makes it a cosmic host, a silent and humble partner to every other molecule on this planet. We have been traveling through the tranquil world of water, that humble liquid that holds so many secrets. Now let's rise above it and turn our attention to the vast invisible blanket that wraps our entire planet, the atmosphere. This is not just empty air. It is a living, breathing chemical system, a thin, delicate skin that protects us from the harshness of space and makes life on the surface of our planet possible. This is the breath of the planet, a symphony of gases in a constant state of motion and reaction. The air you are breathing right now is not a simple substance. It is a mixture, a gentle blend of gases. 78% of it is nitrogen, a quiet, unassuming gas that is relatively unreactive. It serves as a kind of atmospheric buffer, a serene backdrop for all the other, more dramatic players. 21% is oxygen, the life giver, the energetic one, and the remaining 1% is a cocktail of other gases including argon, carbon dioxide, neon, and most importantly, water vapor. Each of these gases has a part to play in the grand atmospheric drama. The most vital chemical exchange in our atmosphere happens quietly every second of every day right at your fingertips. It is the dance between photosynthesis and respiration. Photosynthesis, which we can think of as a quiet form of alchemy, is how plants take sunlight, water, and carbon dioxide and turn them into sugar and oxygen. The carbon atom from the air is woven into the plant's structure, storing the sun's energy in a chemical bond. Then, in a process that is the mirror image of photosynthesis you and I breathe in, that oxygen break down the sugars from the food we eat and exhale carbon dioxide back into the air. We are quite literally exhaling the carbon that a plant inhaled. It's a perfect closed loop, a quiet exchange of gases that links all living things. A little-known fact about this process is just how much it has changed the planet. When the Earth was young, its atmosphere had almost no oxygen. It was a very different and, for us, a very hostile place. Then, about 2.5 billion years ago, a type of bacteria called cyanobacteria began to evolve. They had a new trick: they could use sunlight to create energy, and they released oxygen as a waste product. This was the Great Oxidations event. The oxygen, which was toxic to most life at the time, slowly built up in the atmosphere, eventually making it possible for us to evolve. The very air we need to survive was once a dangerous chemical pollutant released by tiny, tireless microbes. The history of our atmosphere is a story of gradual, profound chemical transformation. This slow, constant chemical dance extends beyond just living things. Consider the water cycle. When the sun's warmth hits the oceans, water molecules held together by those elegant hydrogen bonds we talked about gain enough energy to escape as vapor. This is evaporation. The water vapor, a gas, rises into the cooler upper atmosphere. And in a process called condensation, the water molecules lose that energy, slow down, and cluster together around tiny particles of dust or salt in the air, forming clouds. Those clouds, in turn, can become rain or snow. It's a continuous planet-wide chemical and physical transformation, moving water from the oceans to the air, to the land, sculpting landscapes, and sustaining life as it goes. But the atmosphere is not just a passive medium. It is a reaction chamber. Think of lightning, a sudden, powerful electrical discharge. As a historical note, the ancient Greeks and many cultures after them believed lightning was a weapon of the gods. They were not entirely wrong. It is a powerful force, but a philosopher would tell you that it is also a chemical event. The immense energy of a lightning bolt can break the very strong bonds of the nitrogen gas in the air, forcing it to react with oxygen. This creates nitrogen oxides, which eventually fall to the ground in rain, acting as a natural fertilizer for plants. A flash of light in the sky, a sound of thunder in chemistry, is at work enriching the soil for the forests and fields below. And what about the winds? The winds are a physical expression of a chemical truth energy. From the sun is not distributed evenly. The equator gets more heat than the poles. This temperature difference drives convection currents, as warm air rises and cool air sinks, creating large-scale circulation patterns. These currents are also responsible for carrying moisture pollutants and dust all around the globe. This is why a volcanic eruption in one part of the world can affect weather patterns and air quality on the other side of the planet. Our atmosphere also has a protective shield that is itself a chemical creation, the ozone layer. High up in the stratosphere, sunlight strikes oxygen molecules, breaking them apart. The lone oxygen atoms then combine with other oxygen molecules to form ozone, a molecule with 3 oxygen atoms. This ozone then absorbs powerful ultraviolet radiation from the sun, protecting us from its harmful effects. In a sense, it's like the universe's own natural sunscreen. But, as you know, our modern chemistry has created some unintended consequences. Chlorofluorocarbons, or CFCs, once used in refrigerators and aerosol sprays, were found to be very good at breaking down ozone. This led to a large hole in the ozone layer, a serious problem that was only addressed through global cooperation. The academic debate about whether the hole would have healed on its own is still a subject of some discussion in scientific circles. But the consensus is that human intervention was critical. It is a cautionary tale of how one small chemical change can have vast global effects. The atmosphere is a delicate balance, a quiet and constant negotiation between gases, energy, and life. From the gentle rustle of leaves in the wind to the spectacular colors of a sunset, we are witnessing chemistry in action. The reds and oranges of a sunset are caused by the scattering of light by dust and other particles in the atmosphere. A physical phenomenon, but the colors are also a reminder that the light itself is a kind of energy that powers all the atmospheric chemistry we've discussed. So as you breathe in and out, remember, you are participating in a conversation that is as old as life itself. You are part of the breath of the planet, a chemical reaction that links you to every tree, every microbe, every cloud in the sky. It is a quiet, continuous process, a reminder that we are not separate from the natural world, but an intricate, beautiful, and temporary part of it. We've floated on the air and the water, tracing the great cycles that keep our planet alive. Now, let's descend. Let's go deep beneath the surface, past the soil, past the roots of trees, into the very bones of the earth itself. Here in the quiet darkness, chemistry takes on a different rhythm. It is a slow, patient, and monumental dance that spans not seconds or hours, but millions of years. This is the world of geochemistry, the silent, tireless engine that builds mountains, carves canyons, and gives our planet its very shape, the Earth's crust. The thin, fragile skin that we live on is a testament to the patient power of chemical change. It is made of rocks and minerals, each one a unique chemical compound. And these compounds are never truly at rest. Consider a single rock lying on a mountainside. It seems inert, timeless, but it is in a constant dialogue with the elements around it. Rain, a weak acid, it falls on the rock. It reacts with the minerals inside, slowly breaking them down. This process, known as chemical weathering, is the ultimate act of patience. It can take centuries to break down a small boulder into sand, a process that is in essence a series of tiny, gentle chemical reactions. For instance, a common mineral called feldspar reacts with carbon dioxide dissolved in rainwater, slowly transforming into clay and releasing ions into the soil. It's a fundamental process that turns the hard, solid rock of the mountains into the soft, fertile soil that sustains life. A fun historical aside, the ancient Romans had a curious understanding of this. They noticed that their marble statues and buildings over centuries began to lose their sharp edges and smooth surfaces. They attributed this to the breath of time, or the tear of the heavens, a poetic but incorrect explanation for what was in fact a very slow acid-base reaction. The acidic rain was slowly dissolving the calcium carbonate in the marble, a chemical process that was simply too slow for them to fully grasp. The lesson: the grandest chemical dramas often unfold at a pace too leisurely for the human eye to perceive. This gentle weathering doesn't just break things down, it recycles them. The ions and minerals released from the rocks are carried by rivers to the oceans. There they become part of the great oceanic soup, a vast chemical solution that is home to countless life forms. Organisms like corals and shellfish, in a beautiful act of biological chemistry, pull those dissolved calcium and carbonate ions from the water to build their shells. When they die, their shells fall to the ocean floor, where over millions of years, the immense pressure and heat of the earth turn them into rock again, forming massive deposits of limestone. This is the Earth's quiet, elegant way of taking atoms from the air and rock, putting them into living things, and then burying them for the long future. One of the most profound and still hotly debated topics in geochemistry is the carbon cycle. We talked about how carbon moves between the atmosphere and living things, but there is a much slower, more ancient geological cycle at work. Carbon dioxide from the atmosphere dissolves in rainwater to form carbonic acid. This acid weathers the rocks, and the carbon is eventually transported to the oceans. It gets incorporated into the shells of marine organisms, which, as we saw, eventually become limestone. That limestone can then get buried deep in the Earth's crust, where immense heat and pressure can melt it, and the carbon can be released back into the atmosphere through a volcanic eruption. It is a slow, ponderous loop that connects the air, the ocean, the land, and the fiery heart of our planet. A major point of academic debate, however, is the exact speed of this process. Some scientists believe this geological cycle is a kind of natural planetary thermostat automatically adjusting the level of atmospheric carbon dioxide over immense timescales. Others argue that its pace is too slow to counteract the rapid human-caused changes we see today. It is a mystery that science is still very much trying to solve. Of course, not all geochemistry is so quiet. Deep beneath the crust, the Earth's interior is a seething cauldron of chemical change. The immense pressure and heat melt rock, turning it into magma. This magma, a complex chemical solution, can then erupt from volcanoes, bringing ancient materials to the surface. Each type of volcano, from the explosive volcanoes of the Pacific Ring of Fire to the gentle flowing volcanoes of Hawaii, is a product of a different kind of geochemistry, a different blend of minerals, gases, and heat that determines how it will behave. And even in a seemingly stable place, like a desert, geochemistry is at work. The beautiful, delicate crystals of gypsum and salt that form on the surface are a product of evaporation. As water evaporates from a shallow lake, it leaves behind the dissolved minerals, which then crystallize, a silent act of chemistry that creates exquisite but often fragile works of art. A little-known fact about these desert crystals is that some of them, like the desert roses of gypsum, have been found with pockets of ancient water trapped inside. These tiny, perfectly sealed time capsules can contain water from millions of years ago, a literal geological memory preserved by the laws of crystallization. So when you see a mountain, you're not just looking at a pile of rock. You're looking at a story of ancient chemistry and slow, relentless change. The soil you walk on is the byproduct of countless chemical reactions that have been happening for millennia. The sand on a beach is the remains of a mountain patiently broken down and sorted by wind and water. The very ground beneath your feet is a living, breathing chemical system, and you are a part of its story. It is a comforting thought, isn't it? To know that even in the most solid, unchanging parts of our world, there is a quiet, constant conversation happening at the molecular level. Rocks speak to rain, rivers speak to oceans, and oceans whisper to the sky. It is all a part of the same great chemical symphony, a symphony that, for all its immense power, is often so quiet, you have to listen very, very closely to hear it. We have descended into the quiet, ancient rhythms of the Earth's geology, and we have seen how patient and timeless chemistry can be. Now it's time to turn to a kind of chemistry that moves at an entirely different pace, a chemistry that is intricate, astonishing, and happening inside you right now. This is the world of biochemistry, the soft hum of life itself. It's the quiet, meticulous choreography of molecules that allows you to breathe, to think, and to dream. Think of your body not as a solid form, but as a vast interconnected chemical laboratory. Every cell, every organ, every muscle is a tiny chamber where millions of reactions are happening in perfect harmony. And unlike the grand slow movements of geochemistry, these reactions happen in milliseconds, orchestrated with an elegant precision that still baffles scientists. At the heart of this molecular symphony are three main players: proteins, DNA, and ATP. Let's start with proteins. We often think of them as simple building blocks, the stuff of muscle and hair. But in the world of biochemistry, they are the tireless workhorses, the Swiss Army knives of the cell. A protein is a long chain of smaller molecules, called amino acids, folded into a fantastically complex and specific three-dimensional shape. This shape is everything. It's what allows a protein to do its job, whether that's to act as a structural support, a messenger, or most importantly, a catalyst. These special protein catalysts are called enzymes. Enzymes are the master orchestrators of biochemistry. They speed up reactions that would otherwise take days, years, or even centuries, making them happen in the blink of an eye. Each enzyme is specifically designed to work with one or a very small number of other molecules. You can think of it like a key and a lock. The enzyme's shape is the lock, and the molecule it acts on is the key. They fit together perfectly, and when they do, the enzyme can gently twist or nudge the molecule, making it easier for a reaction to occur. A historical note here: for a long time, the life-giving processes of the body were seen as a kind of magic or vital force that was separate from the laws of chemistry. It wasn't until the 19th and early 20th centuries, with the pioneering work of scientists like Louis Pasteur and later biochemists, that we began to understand that life itself is a chemical process. There is no magic, only an astonishingly complex and elegant set of reactions. Now, where do the instructions for these intricate proteins and enzymes come from? That's the role of DNA, the magnificent spiral staircase of life. DNA, or deoxyribonucleic acid, is the grand architect. It is a molecule that stores all the instructions for building every protein in your body. It is made of just 4 simple chemical building blocks arranged in a specific sequence. This sequence is a code, a kind of biological language that tells the cell exactly what amino acids to use and in what order to create a specific protein. It's a miracle of information storage and a truly beautiful piece of molecular engineering. This quiet, unassuming molecule, curled up in the nucleus of every cell, holds the blueprint for your entire being. But a blueprint isn't enough to build a house. You also need energy. And that's where ATP comes in. Adenosine triphosphate is the universal energy currency of the cell. It's a small, elegant molecule that stores energy in its chemical bonds. When a cell needs energy to move, a muscle, send a signal, or build a new molecule, it simply breaks one of those bonds, releasing a small, usable packet of energy. Once that energy is used, the molecule becomes ADP, adenosine diphosphate, which can be recharged, later ready to be used again. It's a perfect rechargeable energy unit that powers nearly every process in your body, from the firing of a neuron in your brain to the beat of your heart. An academic argument still lingers over whether ATP is a true currency or simply a high-energy molecule, but its essential role is undisputed. The entirety of these reactions, the building up of complex molecules and the breaking down of others for energy, is called metabolism. It's a constant organized chemical flux. On the one hand, you have catabolism, where things are broken down. When you eat a snack, your digestive enzymes break down the large molecules of food into smaller ones, and your cells, in a process called cellular respiration, break down sugars to release energy. On the other hand, you have anabolism, where things are built up. Your cells use the smaller molecules and the energy from catabolism to build new proteins, repair tissues, and grow. It's a perfect balance, a cycle of destruction and creation that keeps the system running smoothly. A particularly fascinating and little-known detail about biochemistry is the role of something called chaperone proteins. As new proteins are being made, they sometimes fold into the wrong shape, which can make them useless or even harmful. Chaperone proteins act as guides, wrapping around the new protein and helping it to fold correctly. It's like having a team of gentle assistants, making sure the molecular assembly line is working perfectly. Without them, a single mistake in a protein's folding could lead to a cascading failure of the entire system. So as you lie here, remember what's happening beneath your awareness. Your brain is thinking a process powered by ATP firing across neurons. Your heart is beating a muscle, contracting and relaxing due to a delicate balance of ions and proteins. Your body is silently repairing itself, molecule by molecule. It's all biochemistry. It's a quiet, tireless, and astonishingly beautiful process that connects the macro world of your experience with the micro world of your atoms. You don't feel the enzymes working, you don't see the DNA unzipping, and you don't hear the hum of ATP cycling through your cells. But it is all happening, a symphony of a billion tiny actions, all working together in perfect, silent harmony. Your life is not a magical force. It is an incredibly complex, finely tuned, and endlessly elegant chemical process. And there is a deep sense of peace in that thought, knowing that you are a part of this ancient, ongoing molecular dance. We have traveled from the cosmic beginnings to the quiet, ceaseless work within our own bodies. Now let's turn our gaze inward to the most mysterious and intimate chemical realm of all the senses and the mind. It is here that the cold, silent logic of atoms and molecules transforms into the warm, vibrant reality of our consciousness. The thoughts you are thinking, the emotions you feel, the memory of a summer day, all of it is a beautiful, intricate act of chemistry. This is not magic. It is an extraordinary, elegant kind of chemistry, a silent conversation between molecules. Your brain, that magnificent organ, is a dense network of neurons, and every thought, every feeling, every memory is a tiny electrical signal traveling along these pathways. But what powers these signals? It all comes down to a delicate chemical dance across the cell membranes of your neurons. A neuron at rest has a specific balance of positively and negatively charged ions, like sodium and potassium. It's a bit like a battery with a positive side and a negative side waiting for a spark. When a signal arrives, it triggers the opening of tiny protein channels in the cell membrane. Positively charged ions rush in, causing a rapid shift in the neuron's electrical charge. This is a chemical change, a sudden fleeting exchange of ions. That change then triggers the next channel to open and the next, creating a wave of electrical activity that travels down the length of the neuron. This is an action potential, the very language of the brain. It's a quick, decisive chemical event that we experience as a lightning-fast thought or a reflexive action. When the signal reaches the end of the neuron, it doesn't just jump to the next one. There's a tiny gap between neurons called a synapse. To cross this gap, the neuron releases special molecules called neurotransmitters. These neurotransmitters float across the synapse and bind to receptors on the next neuron, like a tiny chemical key fitting into a lock. If the fit is right, it triggers the new neuron to fire, and the signal continues on its way. This chemical relay is happening billions of times per second in your brain. Serotonin, dopamine, endorphins. These are not just abstract concepts. They are physical molecules, each one with its own unique shape, its own unique role, and its own unique story to tell. Let's think about your senses. They are all at their core chemical reactions. The very act of sight is a chemical one. When a photon of light enters your eye, it hits a molecule called retinal inside a protein called rhodopsin. That single photon of energy causes the retinal molecule to change shape. This change triggers a cascade of chemical reactions, which eventually leads to an electrical signal being sent to your brain. Your brain then interprets that signal as light, a single fleeting quantum event, a chemical change in a single molecule, becomes a part of your perception of the world. And what about taste and smell? They are purely chemical. Your tongue and the inside of your nose are lined with millions of specialized receptor cells. When a food molecule, for instance, enters your mouth, its unique shape fits into a specific receptor on your tongue. The binding of that molecule to the receptor triggers a chemical signal that your brain interprets as sweet, sour, salty, bitter, or umami. The smell of fresh-cut grass, the taste of a hot cup of tea, the aroma of a pine forest, all of it is a series of chemical keys fitting into a series of molecular locks. A historical diversion for centuries, philosophers debated the nature of consciousness and the senses, with many believing they were non-physical phenomena, gifts from the gods, or expressions of a spirit. The idea that something as profound as love or memory could be a result of molecules floating around in a liquid-filled sack seemed ludicrous. It wasn't until the 19th and 20th centuries, with the pioneering work in neurochemistry, that we began to understand the profound, beautiful connection between the material and the immaterial. The debate over whether consciousness itself can be fully explained by chemistry is still a point of fierce academic discussion. But it's undeniable that the language of our inner world is written in the alphabet of atoms. One of the more quirky facts about this is the incredible sensitivity of some of our senses. Did you know that your nose can detect a single molecule of certain scents? Or that the human eye is so sensitive it can theoretically detect a single photon of light in the dark? These are not exaggerations. Our senses are finely tuned chemical instruments honed by millions of years of evolution to interact with the world around us. Your ability to detect the faintest scent of wood smoke or to see a faint star in the night sky is a testament to the elegant, delicate power of chemistry. This gentle ballet of molecules and ions is not just about our perception of the world. It is also about our feelings and our moods. Hormones like dopamine and serotonin are neurotransmitters that play a huge role in how we feel. When you feel a sense of well-being after a good run, it's a flood of endorphin molecules filling receptors in your brain. When you feel a deep sense of connection, it's oxytocin molecules at work. These aren't just feelings. They are real physical molecules, and their presence or absence has a profound impact on your experience of the world. So as you lie here listening, a tiny part of the universe is becoming aware of itself. A collection of atoms and molecules, following the timeless rules of chemistry, is generating thoughts, memories, and emotions. The oxygen you breathe, the sugar you ate for dinner, the water that makes up your brain, all of it is being woven into the fabric of your consciousness. There is a deep peace in this thought. You are not a ghost in a machine. You are the machine, and the machine is made of stardust and dreams. The very act of thinking is a beautiful chemical event, a kind of magic that is more real and more extraordinary than any fable. We have explored the chemistry of consciousness, the intricate fleeting reactions that give rise to our thoughts and feelings. Now let's pull back from the microscopic and look at a grand and often overlooked concept in the universe's story: time. In the world of chemistry, time is not just a constant ticking clock. It is a variable, a gentle force that can either rush a reaction to a fiery conclusion or allow it to unfold with the unhurried patience of a glacier. This is the alchemy of time, the dance of reaction rates that shapes everything from a single flame to the very face of a mountain. Consider two things: a log and a pile of sawdust. Both are made of wood, a collection of the same carbon, hydrogen, and oxygen atoms. Both are perfectly capable of burning. Yet if you try to light the log, it burns slowly with a gentle flickering flame. But if you were to toss the sawdust into a fire, it would ignite in a single explosive burst. The difference is not in the chemistry itself, but in the reaction rate, the speed at which reactants are converted into products. The sawdust with its massive surface area allows oxygen to reach all the wood at once, rushing the reaction to a swift conclusion. The log with its compact form forces the reaction to proceed slowly, one layer at a time. It's a simple lesson: surface area matters, but that is not the only thing that dictates the pace of a chemical reaction. Temperature is a master manipulator of time. Think of that log again. If you leave it in a cold, damp forest, it will decompose, a very slow chemical reaction that can take decades. But if you put it in a fire, that reaction is sped up 1,000,000 times over. This is because heat is a form of energy. When you add energy to a system, the molecules move faster, collide more often, and most importantly, they collide with more force. This increased energy gives the molecules a better chance of overcoming the activation energy, that invisible hill they must climb before they can transform. So a hotter system is a faster system, a truth that applies to everything from cooking food to rusting metal. A particularly fun and little-known fact about reaction rates involves fireflies. These beautiful insects produce light through a chemical reaction in their bodies. They have a molecule called luciferin and an enzyme called luciferase. When oxygen is introduced to the mix, the enzyme catalyzes a reaction that releases light. But here's the kicker. The efficiency of this reaction is so high that it produces almost no heat. It is what scientists call cold light. A perfect, gentle chemical reaction. A miniature light show that is a beautiful testament to the elegance of biochemistry. Concentration is another quiet factor that governs the flow of time. A more concentrated solution has more molecules packed into a given space. This means more frequent collisions, and more frequent collisions mean a faster reaction. Think of a crowded bus station. The chances of bumping into someone are much higher than they are in a wide-open field. The same applies to molecules. This is why a concentrated acid reacts more vigorously than a diluted one, and why in the world of industrial chemistry, carefully controlled concentrations are key to getting a reaction to proceed at a usable and predictable pace. The academic debate about the precise mathematical models of reaction rates has been a long and rich one. For centuries, chemists worked on empirical models based purely on observation. It wasn't until the early 20th century that the theory of collision theory and transition state theory began to give us a real glimpse into the microscopic reasons for why reactions have a specific speed. This is a field where the theoretical and the practical are in constant dialogue, a dance between what we observe and what we can prove. But what about the reactions that seem to never happen? The ones that are so slow, they are for all practical purposes frozen in time. Consider a diamond. A diamond is a form of pure carbon, and it is thermodynamically unstable. Over an unimaginably long period, it will in theory turn into graphite, the soft material in your pencil. But the activation energy for this reaction is so incredibly high that it would take billions of years for it to happen. It is a reaction that is possible, but so slow that it is essentially a non-event. This is a beautiful reminder that in the world of chemistry, the word forever has a very real meaning. This patience, this slowness is everywhere. The weathering of a statue, the formation of fossil fuels, the aging of a fine wine. All are chemical reactions unfolding on a timescale that is both grand and humbling. It is a reminder that the world is in a constant state of change, even when it appears to be perfectly still. The reverse is also true. A reaction can happen so fast that we can barely perceive it. An explosion is nothing more than a chemical reaction with an incredibly fast reaction rate, releasing all its energy in a single brilliant moment. The flash of a camera, the combustion of gasoline in your car's engine, the firing of a rocket. These are all chemical reactions that are being rushed to their conclusion, their speed carefully controlled by engineers and scientists. A historical aside, the use of controlled explosions in mining and construction has been a part of human history for centuries. The use of black powder and later dynamite was a practical application of a simple chemical truth. If you pack things tightly and provide enough energy, a reaction can happen so quickly that it generates enough force to move mountains. So as you lie here, remember that time is a quiet collaborator in every chemical reaction. It can rush things to a conclusion, or it can allow them to unfold at a leisurely, patient pace. It is a silent partner to every atom and every molecule, allowing them to follow their destiny at their own pace. And in a world that often rushes, there is a deep sense of peace in knowing that some of the most profound chemical changes are also the most patient. We have come to the final chapter of our journey. We have traversed the cosmos, delved into the heart of atoms, and meditated on the intricate chemistry of life. We have seen the grand and the small, the fast and the slow, the cosmic and the personal. Now, as we prepare to drift off, let's bring all of these threads together. Let's find the quiet, unifying truth that lies at the heart of everything we have explored. All of this, every bit of it, is connected. The iron in your blood was forged in a supernova, a brilliant cosmic chemical reaction that happened billions of years ago. The water in your cells, that elegant polar solvent, fell from the sky as rain and may have flowed in ancient rivers before it became a part of you. The carbon that forms the backbone of your DNA was once a part of a tree, or perhaps even a dinosaur, a testament to the patient, unending cycle of life. We are not separate from the world around us. We are an exquisite, temporary, and beautiful arrangement of it. Think back to the very beginning. Remember those first hydrogen atoms drifting in the quiet, dark universe. They were lonely, incomplete. Their story was a search for connection, for stability. And that desire, that simple chemical longing, is the same force that drives everything we have discussed. It is the reason bonds form, the reason energy is released, the reason the universe is not just a chaotic mess of particles, but a symphony of elegant, interconnected systems. The beauty of chemistry is that it is not about chaos. It is about order. It is about particles finding their place, about systems finding a state of equilibrium, about energy being released or absorbed in a perfect, elegant balance. When you light a candle, you are not creating fire out of nothing. You are simply providing the activation energy for a chemical reaction that has been waiting to happen. And when the flame dies, the atoms do not vanish. They simply form new bonds, a different arrangement, a new story. Even in the quietest moments, the universe is humming with this activity. The molecules in the air you are breathing are in constant random motion, colliding with each other billions of times a second. The atoms in the pillow beneath your head are gently vibrating in their stable lattice. And within your own body, a silent, continuous conversation is happening at the molecular level, a symphony of biochemistry that is keeping you alive and well. A philosophical aside, the ancient alchemists, for all their magical thinking, were not so far from the truth. They believed in a grand secret unity of all things, in a world where everything could be transformed into everything else. They sought to turn lead into gold, a seemingly impossible task. But as we have learned, the universe does just that on a scale that they could have never imagined. A star takes the simplest element and through the magic of nuclear fusion, turns it into gold. The chemistry of the cosmos is the ultimate alchemy, a continuous and magnificent transformation that connects all matter to all other matter. And this brings us to a beautiful and very real sense of peace. The world is not something to be feared. Its laws are not harsh and unforgiving. They are elegant, logical, and trustworthy. They are the same everywhere, from the fiery heart of a star to the quiet stillness of your own body. The same forces that hold a star together also hold you together. The same laws that govern the tides of the ocean also govern the flow of energy in your cells. You are not a stranger in this universe. You are a part of its most intimate and beautiful story. I hope this journey has been a gentle one for you. I hope it has been interesting, but not so interesting that it kept you from resting. And if it did keep you awake, well, at least you have learned something new about the world and perhaps about yourself before you finally drift off. Or if you're still peacefully listening with your eyes closed, I'd love to know. Where in the world are you tuning in from? What time is it where you are? Are you curled up in bed under soft blankets or on the couch with a pet? Are you hearing the hush of night outside your window or the quiet hum of a distant city? Let me know in the comments. I love hearing where this chemistry journey has taken you. And if you enjoyed this exploration, if you found it relaxing, interesting, or gently thought-provoking, please consider giving this video a like or subscribing to the channel. It helps me bring more of this content to you, and it lets me know that these gentle dives into science are bringing a little more wonder into the world. Thank you so much for being here and for joining me in this quiet celebration of how the universe works one invisible reaction at a time. And remember, even when nothing seems to be happening, chemistry is always happening. The atoms are still dancing, the molecules are still mingling, and the world, even in perfect stillness, is still beautifully, endlessly alive.